very good day, Abid, to our wonderful lecturer and also my wonderful colleagues. On this wonderful day, I would like here to present about our fluid mechanical lab 2 on the immerse of water. Okay, for the first part, we'll be moving on to our abstract. In order to fulfill the requirement of subject, Engineering Mechanics Lab BMM 3521, we had been conducted and come out with this report as the very first lab as we are conducting the term. The title of the experiment investigation the flow pattern over the different immersed body. Okay, for the lab experiment focus on the investigation of flow patterns over different immersed body in which the simulation are done using the airflow bench. There are various models have been tested to the develop understanding and proper modeling techniques and flow around the suggest body. Throughout the experiment, our group of three wanted to determine the body layer thickness of the flat plate subjected to the longitudinal flow for the rough and the smooth surface. For each example, solution obtained were being proposed. Immerse bound methods are compared with solutions on body commercial mass having a comparable mass size distribution. The purpose approach is very accurate and effective in capturing the sharp discontinuity in the normal temperature gradient at the interference.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Arif from AZRY and my metric ID is 18176. So I want to present about the introduction. For the introduction, the purpose of measuring the boundary layer of a flat plate is to investigate the characteristic of boundary layer development, as well as the parameters and the characteristic of fluid flow over a flat plate. This experiment was carried out in the wind tunnel at UMP Turbo Machinery Laboratory. Reading of the boundary layer measurement were taken at 3 different frequencies along a flat plate, which is 15 Hz, 20 Hz, and 35 Hz. The height of the boundary layer grows along the flat plate range from 0.935 mm to 1.021 mm at the frequency 15 Hz, 0.985 mm to 1.025 mm at the frequency 20 Hz, and 0.825 mm to 0.987 mm at the frequency 25 Hz. The values of the displacement thickness and momentum thickness were calculated using the velocity profile and the numerical method analysis. So we go to the next part, which is background statement. So for the background statement, external flows pass an object encompass a wide range of fluid mechanic phenomena. The flow field appearance is determined by the shape of the object. Even the most simple shaped object, such as a sphere, generate radial complete flow. The flow pattern and related forces for a given shape object are strongly influenced by various parameters such as size, orientation, speed, and fluid properties. The study of flow around immersed body has a wide range of engineering applications, but spheres are the most important in terms of heat and mass transfer. So the next part is objective. First objective is to design and evaluate a complete measurement technique experimental procedure for a fluid flow, as well as to measure the drag and lift forces applied to a symmetrical aerofoil at various angles of attack. Second objective is to calculate the velocity distribution and boundary layer thickness of a fluid plate subjected to a longitudinal flow with raw and smooth surfaces. For the scope, many technical applications involve the flow of fluid with low velocity value and thus very high Reynolds numbers. As demonstrated in the previous chapter's example, the limiting solution Re is equal to infinity, which is frequently a good approximation. The no-slip condition is not satisfied by this limiting solution, which means that the velocity at the wall are not zero but infinite. To satisfy the no-slip condition, the viscosity must be considered. This handles the velocity transition from the limiting solution finite value near the wall to zero directly at the wall. At high Reynolds numbers, this transition occurs in a thin layer close to the wall, which is L prime refers to as the boundary layer or frictional layer. As will demonstrated, the boundary layer becomes thinner as the Reynolds number increases.
Okay, moving on to my second chapter will be about the theory of immersed body. Okay, when the object is completely surrounded by the fluid and the flows are extreme external flow, Lift and drag is also called in the fluid force. Theoretically, in the term of analytically and numerical techniques and experimental approaches are used to obtain the information on the fluid force developed by external force. One of the methods to obtain the flow data is by using wind tunnel testing work. In the years of 1990s, the first invention of a car and in a second invention of a bus, where the full-scale wind tunnel test was done to the car, which been used in the drag for racing purposes. Moving on to the second part will be the model scale of the wind tunnel test done to the bus for transportation in the earlier stages of 1990s. And the And the third point will be two-dimensional objects that identify infinity longs and constant cross-sectional size and shape. What here the thing means a dimensional of the infinity long and the constant cross-sectional size of the shape also is the main purpose of the body immerse function. An axis symmetry body formed by the rotating the cross-sectional shape of the axis of the symmetry. When the moving of an object with the number of axes of symmetry increases, where the body immerses of the fluid also increases and make a collision with the friction and may stop or may even eventually can slow down the object from moving in a fast speed. Moving on to the third point with 3D three-dimensional body that may or may not process in the line of plane of the symmetry, as it's mentioned in the point 2, where the symmetrical axis of symmetry also is a main point where the object can be moving away from the direction or even away from the line of plane of the symmetry.
Let's proceed with the methodology. For this lab session, we do two experiments. For the first experiment, which is the flow pattern of symmetric aerofoil at different angle of attack, firstly we set up the experiment. Then we attach and screw the aerofoil model to the airflow bench. Start the experiment with a 0 degree angle of attack. The switch is turned on and the radial fan is allowed to move. Adjust the radial fan speed controller at an initial of 12. Record and tabulate the readings. The smoke controller is then pressed to emit smoke into the flow to view the flow of the air on the aerofoil. Take the picture of the flow of the aerofoil. Increase the radial speed fan controller by 1 till the speed is at 19. Repeat the experiment with different angle of attack, which is 30 degree and 45 degree. For the second experiment, flow over flat plate. Firstly, set up the experiment. Then insert the smooth surface flat plate into the airflow bench. The first distance is taken as 0 and then the following distance taken. Connect the pitot tube to the vernier calipers. The pitot tube is first touched to the surface of the flat plate as the first data. Turn on the radio fan and record and tabulate the data. The distance of the plate is taken from 0 mm, increased by 20 mm to 140 mm, while the pitot tube distance from the surface of flat plate is taken from 4 mm, increased by 4 mm to 32 mm. Repeat the experiment for the rough surface. The results from the first experiment after tabulated. In the experiment 1, we can see the lift and drag coefficient is directly proportional to the lift and drag force. At the beginning, the lift force is greater than drag force, causing the aerofoil to lift up. However, as the angle of attack increases, the lift force started to decrease while drag force increases. For the experiment 2, we divided the experiment into 2A and 2B. For the 2A, smooth surface flat plate. From the data that we recorded, we create a graph of the height, velocity and Reynolds number versus boundary layer. For the experiment 2B, which is rough surface plate, we also plot graph according to the data that we have received. Based on the experiment 2, the boundary layer of the smooth and rough surface are affecting the velocity of the airflow. Both velocity of airflow on smooth and rough surface increase when the boundary layer thickness increase. Even though both 2A and 2B increases in terms of the velocity of the airflow, the velocity of the airflow on smooth surface increase more than rough surface.
Okay, for my last part of the presentation and also our lab experiment will be the conclusion. Okay, on the conclusion, based on the experiment conducted by the three of us, we had been concluding that the drag coefficient is directly proportional to the lift drag force. Our first point is that at the beginning, the lift force is greater than the drag force in the order to lift the airfoil up to the sky. The lift decreases at the 45 degree, but the drag continues to increase because of the air resistance surrounding the airfoil. Meanwhile, in experiment 2 or the attempt 2, the velocity of the airflow has been obviously affected by the boundary layer of the smooth and rough surface plates. The velocity of both the smooth and the rough surface increases across the boundary layer thickness, but the velocity of the smooth surface is much higher than the rough surface because there is resistance in the rough surface that reduces the velocity of the air, which made us to conclude that the drag coefficient is directly proportional to the lift and the drag force, which makes the lift increase where the lift decreases at the 45 degree, but the drags continue to increase, which eventually and proofly has been proved by that saying that the drag coefficient is directly proportional to the lift and drag force. That's all from us. Thank you for listening.